So in Unit 11, we are going to go over the molecular structure. We're going to look and discuss the valence bond model and the valence bond theory to help us better understand and have a complete understanding of the covalent bonding and how the covalent bond forms. Some of the concepts that we're going to go over in Unit 11 or in today's lecture, it might not sound strange to you, especially when we talk about the Lewis structure and the covalent bonding and the valence electrons. What we will do at this point, however, we're going to take a deeper look into the valence electrons and how the valence electron determine what and how many bonds are going to have, specific elements will have, and also how the geometry for molecules are determined based on the valence electrons, based on the paired and non-paired electrons. Okay, so the goal here is to begin to understand why atoms form bonds in the way that we see them. So, for example, when we looked at the covalent bonding in chapter 3, um, we looked at the valence electrons and we said something like carbon will always form four bonds, something like oxygen will always form two bonds or will have two paired electrons, and two non-paired electrons, just like with the H2O, if you may remember. So we have the hydrogen, we have the oxygen with two hydrogen on both sides, and we have two non-bonding pairs of electrons. Okay, when we talked about the hydrogen, on the other hand, we said the hydrogen can form only one bond. So, what the valence model or the valence bond theory will give us will explain to us exactly why does oxygen have only two bonds and have two lone pairs. Why does carbon form only four bonds, and in some cases forms double bonds and triple bonds. Same thing with the hydrogen. So that's where the valence bond model is going to help us in terms of bond formation. On the other hand, it will also help us to give a better description to the formation of covalent bond using the valence bond model. So we will look at the orbital diagrams, and we'll see how the orbital diagrams will help us understand the valence bond or how the valence electrons bond together. And then later we would use the Lewis structure, which is something I know that you should be kind of familiar with because, again, we touched upon it in Unit 3. And we will use Lewis structure to determine the geometry for molecules. So based on the valence electrons, based on the bonds that are formed, non-paired electrons, this will, putting all these pieces together, will help us determine the geometry for molecules, and again through the Lewis structure. So when we're talking about the valence bond model, there are advantages and disadvantages from using models in general. This is not specifically for the valence bond, but generally, what models does to us, it really helps us visualize and explain and predict chemical changes. Okay, um, and it's also the process when we start using models to compare models to reality, because again, models is not reality. Models is something that has some similarities of the reality, but it helps us understand exactly what goes in real examples. Okay, so the processes it depicts are sometimes described using the phrase as if. So in many times you will see me, and you will notice that I'll be using the phrase as if, because this may not happen in reality, but we use this model that really fits within the description of the bond formation, and it really makes sense to us. When it comes to studying the chemical properties. So that's why we use as if, because in many times this has not been confirmed completely. Okay, so it does remind us that we do not necessarily think this is what's really happening for real, but we assume based on the model that this is what happens when it comes to electrons and valence electrons bonding together. Okay, models does change over time, so depending on the technologies, on the analysis techniques that are available, models can change over time because, again, maybe in 10 or 15 years from today, we would have better techniques, better instruments available to study chemical and molecules geometry that basically refutes all the models that we have been using. Okay. Um, so that's in terms of models in general. So when it comes to the valence bond model, the valence bond model or the valence bond theory is based on two main assumptions. Number one, that in bond formation, only the electrons with the highest energy will participate in the bond formation. Okay, and when we talk about the highest energy electrons, that means we're talking about the less stable electrons, correct? Because when we say high energy, that means it's less stable. And generally, those electrons tend to be the valence electrons. And those, the name or the concept of valence electron, that should be no strange to you because those are the electrons that exist on the outer orbitals or the outer shell of the electron configuration, and those are the one that is involved in bond formation. Okay, so that's assumption number one. Assumption number two, that covalent bonds usually forms to pair the unpaired electrons. Okay, so when we did the electron configuration, if you may remember, and we said in some cases, when you look at the electron configuration and you look at the orbital diagram to be more specific, you will have some electrons that are non-paired, as we will look in some examples later. Okay, so the non-paired electrons, those electrons always try to look for a partner where they can be paired together in that orbital. So the valence bundle suggests that the covalent bonds usually form to pair the unpaired electrons. If the electrons are already paired in their orbitals, then there is no chance to form a covalent bond. Okay, so these are the two main assumptions for valence bond. First, only highest energy electron will participate in bond formation, or the valence electrons, aka valence electrons, and the covalent bond is formed to pair the non-paired or the unpaired electrons in their orbitals, as we will see in examples. We'll do many examples in a second. For the valence electrons, these are the electrons with the highest energy. Okay, so when we say the highest energy, that means these are the electrons that are further away from the nucleus. So if we have electrons that are sitting in the 1s and electrons sitting in the 2s, the electron sitting with the highest principal energy level, that means the second principal energy level, will be considered as the highest in energy. And those are the further away from the nucleus, okay? So we'll have higher energy, they will be extremely unstable, and they will be participating in chemical interactions. Electrons that is sitting in the first principal energy level in this example tends to be very stable, closer to the nucleus. When we are talking about the nonmetals, right, because we are talking about the formation of covalent bond, and covalent bond forms between nonmetals. Okay, so we are focusing mainly on the P and S block in the periodic table, correct? So if you look at the nonmetals in the periodic table, they all pretty much belong to the P block of the periodic table, except for the hydrogen, which belongs to the S block of the periodic table, and the helium. Okay? Beside that, the boron, carbon, nitrogen, and everyone else, they all belong to the P block of the periodic table. So the highest principal energy level normally for the covalent bond atoms, the covalent bond molecules, we're talking about the S and P electrons in the atom. And the reason why it's an S and P electrons, as I said, because all the nonmetals belong to the P block of the periodic table, or the S block in the periodic table. So that's why we refer to it as the S and P electrons in the atom. So the question becomes, well, how do we determine what is the number of valence electrons? And I think some of you might remember this again from Unit 3, that we'll look at the number of the group where that electron or that atom or that element belongs, correct? So if we look at the boron, for example, we know that boron has a 3 valence electrons. For the carbon, there is 4 valence electrons. So those are the number of electrons will be participating in the covalent bond formation. We care less about the other electrons. Same thing for the nitrogen and everything on the nitrogen group, including the phosphorus and the arsenic, will have 5 valence electron. Oxygen and the element in the group of oxygen will have 6 valence electrons. For the fluorine and the halogens in general, they will have 7 valence electrons and 8 valence electrons for the noble gases, except for the helium that has 2 valence electrons. So this is how we can count the valence electrons, and we can tell how many of those electrons will be participating in the covalent bonding. Okay, so by looking at the periodic table and identifying the number of the group, which represents the number of covalent bonding. So let's focus on the concept of pairing electrons, pairing electrons, pairing the unpaired electrons. First atom that we are going to be looking at is the hydrogen atom. Okay, so this is our buddy from the periodic table that we try to use him as our guinea pig when we talk about models, valence bond model, or even when we did when we studied the electron characteristics, we focus on the hydrogen because it's the simplest in the periodic table. So for the hydrogen, when we look at the electron configuration for the hydrogen, right? So hydrogen has 1s, 1 with one single electron. And again, you can figure that out by just looking on the long periodic table that I provided you in previous lecture. But when we do the electron configuration, it really does not help us to see how the electron is spinning, where the electron is sitting. Well, in this case, it's sitting in the 1s. But if you're talking about like p orbitals, for example, we need to find out exactly how every single electron is sitting in every one of those p orbitals. So what we need to do, in other words, we need to, in addition to writing the electron configuration, we need to write the orbital diagram, because the orbital diagram gives us a good display of where the electron is and how the electron is spinning. So every time you try to do covalent bonding or valence bond model, you need to do the electron diagram, okay? So with the 1s, we have one electron pointing upward. And the point of covalent bonding, again, we are trying to bond or pair the covalent the valence electrons. So in this case, we have one electron here, and we have another hydrogen atom that has only one electron again. So it has the 1s with one electron. So what happens in this case, these two electrons will pair together to form H2. Okay? To demonstrate it in a better way, if you have the hydrogen atom with one s1, and you have the 1s orbital with one electron pointing upward. Again, we have the other hydrogen atom coming in with its 1s orbital. Again, 1s1 electron, and that electron is going to come down here and pair with the second hydrogen atom. In this case, we are going to have H2. That's why hydrogen exists in a diatomic format, because the diatomic format provides the hydrogen with a paired electron. So this is a very stable electron formation. And it is a covalent bond because you have two atoms bonded, two atoms are the same as bonded together. And again, because hydrogen is a nonmetal. Sometimes when we do the Lewis structure or the Lewis dot structure, we present the electron, or we refer to the electron as a single dot. And we have the electron of the hydrogen, same thing with a single dot presenting only one electron. So what happens, what we do is we do this, forming the bond. So we replace these spaghetti lines with a straight line representing the covalent bond between the two hydrogen atoms. Now, again, that's for the hydrogen, the simplest atom we have in the periodic table. Things will get a little bit more complicated when we're talking about something like boron or carbon later. Let's look now at the boron and see how the boron would behave, forming the three bonds, and why boron form three bonds all the time. Um, in order to explain this, what we need to do first, we need to write the electron configuration for the boron. So that is a 1s2. That's a typo. It's not a 1s1. 2s2 and 2p1, because boron has 5 electrons in the periodic table. Okay, so if you follow the long periodic table, this is the electron configuration that you'll be getting. So these are the 3 electrons that really matters to us, because those are the valence electrons. Those are the highest energy, and those are the one that is going to form the bond, either by sharing or by donating. So why are we focused on the boron? A good question would be, why not just study the fluorine, for example, and try, understand why the fluorine formed the bond with the boron. The reason why, because the boron here is the central atom. And always when we try to understand bonding in any molecular structure, we try to focus on the central atom. How do we know the boron is the central atom? Because, again, we determine the central atom based on the subscript. So with the BF3, for example, boron has a subscript of 1, so that makes the boron the central atom. So the atom with the least number of subscripts will be considered the central atom. That's why we're focused on the boron. So if we do the electron configuration, next what we need to do is we need to draw the orbital diagram, because without the orbital diagram, the electron configuration is not sufficient enough to show us where the single electrons are sitting and how the pairing of electrons is going to happen. So the boron orbital diagram without bonding, this is how it's going to look like, with 2 electrons sitting in the s orbital, a single electron sitting in the p orbital. When the boron is excited and it's about to form a covalent bond, what happens, as if the single electron on the s orbital, it is going to relocate to one of the p orbitals. Well, why would something like this would happen in this case? Because once this electron moves to the next p orbital, what happens now, we have 3 single non-paired electrons. That means now we have a room to accommodate for the 3 incoming electrons, 3 incoming atoms with their single electrons. That's why boron would form the 3 bonds. So what happens, now that I have the space to accept the 3 electrons, fluorine or iodine or bromine, anything from the halogen group on the periodic table, it is going to come in with their single electron, as we will look at a fluoride in a second, and they would jump in and pair up with every single electron on the boron orbital diagram. Okay, so these red electrons pointing downward, those are basically the fluorine electrons, the valence electron for the fluorine coming in and pairing with the boron electrons. Okay, that's why when we do the Lewis dot structure for the boron, that's how we do the Lewis dot structure. We do boron and 1, 2, 3, because we focus only on the 3 electrons for the boron, on the valence electron. And then you have the fluorine that comes in with their electrons as well. Okay, so all the electrons here have been paired. We don't have any non-bonding pairs, correct? Do we see any electrons that has just sat around, didn't really get involved in the coupling with the other electron that is coming from the fluorine? The answer is no. So all the electrons has been paired. That's why boron has all bonding pair and zero non-bonding pairs of electrons. That's when it comes to the boron. So this is how the 3 bonds for the boron are usually formed. So for the carbon, we are going, again, what we need to do is we need to identify our central atom. What is our central atom? It is going to be, for the CH4, it is going to be the carbon right here. Why is it the carbon is the central atom? Because it is with the smallest number of subscripts, right? There is 1 for the carbon and 4 for the hydrogen. So hydrogen is going to be bonding to the carbon. First, what we need to do, there's another typo here. This would be N1s2. We need to write the electron configuration for the carbon. Okay, so the electron configuration is a 1s2, as you see here, 2s2, and 2p2. These are the electrons that we are going to focus on, the 2s2 and the 2p2. So if you were to draw the orbital diagram for the carbon, the central atom, you will have 2s orbitals with 2 electrons pointing upward and downward, and you have the 2p orbitals with 2 single electrons both pointing upward, just like that. When the carbon is ready to form a bond, what happens, similar to the boron, the electron, one of the electron on the s orbital, as if it is relocated to one of the p orbitals in the carbon, okay? So this electron would move and travel from the 2s orbital to one of the p orbitals, opening up a space of 4 different incoming electrons for the hydrogen. That's why carbon always forms 4 single bonds, or 2 double bonds, for example. Okay? As I said, we will look at the double bonds and triple bond in a second. So when we draw the Lewis dot structure for the carbon, for example, we do carbon 1, 2, 3, 4, because we try to focus only on the valence electrons. Okay? So now with 4 orbitals with 4 single electrons, these electrons now are prepared to accept incoming electron from another atom. That atom could be hydrogen, for example. So hydrogen now is going to come with its single electron and drop a single electron down here and pair with the valence electrons of carbon at this stage, forming a CH4. Carbon with its single electron. Okay, so carbon would always need 4 hydrogen atoms in order to form the CH4, because carbon would have 4 electrons, 4 non-paired electrons sitting in 4 different orbitals, able to accommodate 4 different atoms for hydrogen to form the CH4. Now, the next couple ones that we'll be looking at, which is the nitrogen and the oxygen, they look a little bit different. The nitrogen and oxygen is one of the atoms in the periodic table that has the lone pairs or the non-bonding pairs of electrons. And we will see those in a second once we understand how the bonds are formed and why do we have these 2 electrons non-bonding at the end when the nitrogen has formed its bonds. Okay. So first, what we need to do, we're studying the NH3, and we want to understand why do we have 3 hydrogens, not 4 or 5 hydrogens, and how those bonds are formed. So first, what we need to do is we need to identify our central atom, and that's going to be our nitrogen, right? Because we have 1 nitrogen, we have 3 hydrogen. Second, what we need to do is we need to write the electron configuration. What is the electron configuration for the central atom? So the electron configuration for the central atom. The electron configuration for the central atom is 1s2, that's another typo, 2s2, and 2p3. So these are the electrons on the on the second principal energy level that we're going to focus on, which is, as you see, 2s and 3 of the p. So that makes it 5 total valence electrons. So this is the count for the valence electrons for the nitrogen. Nitrogen has 5 valence electrons. Nitrogen can form 3 bonds and it has only 1 lone pair. Let's see how that happens. So, and again, once we have the electron configuration, we have to do the orbital diagram. The orbital diagram for the nitrogen with 2s orbitals that has 2 electrons and the 2p orbitals with 3 single electrons. So it looks like the nitrogen already has the space to accommodate the 3 electrons, correct? And that is obvious in the p orbitals. In other words, the s electrons doesn't really get to be involved in this process at all. As a matter of fact, the 2s orbitals can stay as they are at this point. And the nitrogen, the p orbitals in the nitrogen is able to accept the incoming electrons without the involvement of the s orbital. So at this point, we're talking about the hydrogen. The hydrogen is ready to come in with its single electron and form the NH3. So when we do the Lewis dot structure for the nitrogen, we do nitrogen and 1, 2, 3, 4, and we go back and put the 5th electron next to the first one. So that leaves 2 electrons on the top. And that's what we see here. Now these 3 single electrons are ready to be paired with the electrons, incoming electrons from the hydrogen. So that explains why the nitrogen forms the 3 bonds with the hydrogen and leaves the 2 electrons non-bonding on the top, because these 2 electrons represents the 2s electrons because they are not involved in the bond formation of the NH3. So nitrogen will need 3 of the hydrogen to form its stable structure, which is the NH3 with 2 non-bonding pairs. So this is where the lone pairs are coming from. Some books, they will refer to this as non-bonding pairs. Other, they will refer to this as a lone pair of electron. Okay. Let's look at the oxygen. It's pretty much behaves very similarly to the nitrogen. So the oxygen in H2O. So we were looking at H2O. So again, oxygen is our central atom at this point. What we need to do is we need to write the electron configuration for the central atom because that's the one that matters to us. So it's 1s2, 2s2, 2p4. So these are the electrons that we're going to focus on when we study the electron, the structure for the H2O. So oxygen forms 2 bonds and has 2 lone pairs. How does this happen? In order to understand this, what we need to do is we need to write orbital diagram. The orbital diagram for the valence electrons, again, we're doing only the valence. For the valence electrons, we're not doing the whole thing. 1s2, 2p, that has 1, 2, 3, and 4th electron. Now, in order to remember how we do this, so this is the 2s, 1, 2, 3. This is the p. So we have 2 on the 2s. This is the 2p. For the p, we have 4 electrons. Remember, we do singles, and we go back and pair. This is how this orbital diagram was done. Then you have 2 non-bonding pair of electrons sitting on the p orbital. Okay, so remember when we do the electron configuration, when we do the orbital diagram, please consider that when distributing your electrons. Okay, so let's go back to this one. So this is how the p orbitals will look like with two pair of electrons, two pair of electrons here, and we have two single electrons that it's available to accept another electron coming from hydrogen in this case. So as you see here, we already have that space to accommodate for the hydrogen to come in, right? We have the p orbitals that is available to accept the hydrogen atoms without the involvement of the 2s and the 2p orbitals, correct? Which makes the 2s and the 2p orbitals a non-bonding pairs, lone pairs of electrons, because they are not really involved in the bonding reaction between oxygen and hydrogen. That's why oxygen will always need two hydrogens, and then it will have two lone pairs of electrons. So what we do is let's delete this one. So we do oxygen, our central atom, correct? And we have the the two lone pairs, and we have single electrons down here. And that's where the hydrogen comes in. So we have the hydrogen that comes in with a single electron, But what we do, since we have two bonding pair, what we do is we replace this with a straight line. So this is the structure for the oxygen with two lone pairs. These are the lone pairs. It is fundamental that when we do these structures and electron configurations, and at the end when you try to draw the lowest structure, it is very important to indicate to me where's the non-bonding pairs or the lone pairs, okay? Because we need to kind of make those stand out compared to the bonding pairs with the hydrogen, for example. Because in addition to that, later what we will see those non-bonding pair play a key role when it comes to forming the geometry. It will determine what kind of shape this molecule is going to have. Let's look at the fluorine. For the fluorine, same thing. We are doing the F2, and we're going to try to understand why the fluorine forms as F2, not as an F3 or F5. First, what we need to do is we need to determine our central atom. Which one our central atom? There is no central atom because this is a symmetrical molecule between two fluorines. What we need to do next, we need to do our electron configuration. That is supposed to be 1s2. And fluorine can form only one single bond and has three lone pairs. Okay, the orbital diagram for the valence electron would look like this, with 2s electrons, 2s orbital, two paired electrons, and you have 2p orbitals, two of them with two paired electron, which leaves only one single electron that is not paired, ready to accept another electron. So another fluorine is gonna come in with their single electron and pair up with this single electron, forming the F2. That's why when we do the Lewis dot structure, this is how it's going to look like, and this is how it's going to look like for the other fluorine, and both they would come together, and we replace that with a straight line. Okay, so I think we have a couple more examples before we get into this table. So if you may have paid attention at this point, bonding are formed when we have single electrons that it's not paired. So bonds, the main reason to forming bond is to pair single electrons. So another electron would come in and share the electron to form a bond. So the number of bonds is really determined by the number of the single electrons that it's available to pair with the incoming electron. So if you have one single electron, then you will have only one bond. If you have two single electrons, then it'll have two bonds, so on and so forth. We always pay attention to the non-bonding pairs. So in this case, for the fluorine, for example, we have 1, 2, 3. We have 3 lone pairs. So when we say 3 pairs, that means it's 6 electrons. So do not be confused. We commonly refer to the non-bonding electron as pairs. We don't rarely refer to them as singles. We usually refer to them as pairs. So for fluorine in this case, we'll have 3 lone pairs of electrons. Those are not involved in the chemical bonding. So we are always try to find which electrons that are single electrons sitting in the orbital diagram, because this will determine how many bonds that atom is able to form. This table here is from chapter 3, which is a good refresher for the elements and how many bonds it can form and how many lone pairs it will have. Something like carbon will form 4 covalent bonds, right? We just looked at the CH4. Does it have any lone pairs? No, it does not. So it has 0 lone pairs of electrons. That's why when we do the carbon, for example, or if we refer to that one, let's do that as something generic, just like X. So I'll have 1, 2, 3, and 4, accepting 4 different bonds, right? So that's for the carbon. Something like the nitrogen, the phosphorus, the arsenic, everything that belongs to that group would look like this, with 2 electrons and 3 single electrons ready to form 3 different bonds. So that's the case always for nitrogen, phosphorus, and arsenic. We'll have 3 covalent bonds and 1 lone pair. Oxygen, sulfur, and selenium, we have 2 covalent bonds and 2 lone pairs. And we can see that if we do this general formula with 2 lone pairs on the top and 2 single electrons forming the 2 bonds. And that's what we noticed when we did the H2O. The fluorine, chlorine, bromine, iodine, or all the halogens will have 1 covalent bond and 3 lone pairs, which means 6 electrons surrounding the fluorine or the bromine that are not bonding or not involved in the bond formation. So that would have 1, 2, 3, 4, 5, 6, and we have 1 lone pair to form a single bond. Okay, so we have 1, 2, 3 lone pairs. So this is basically a summary of what we just have been discussing regarding the bond formation, the lone pairs, and the bonding pairs. So let's make things a little bit more challenging and try to draw Lewis a little bit more complex Lewis structures. So when it comes to carbon, I think up to this point, we all agree that carbon always forms 4 bonds or 4 single bonds, okay? What carbon is also capable of doing is satisfying that 4 bonds through multiple ways. That can be either by forming 2 single bonds. Let's see. So that can be either by forming 2 single bonds and 1 double bond. So when we say 1 double bond, that means 2 bonds together. So that makes it 4 in total. As we see here, so if you look at this molecular structure down here, you can see carbon. It has 1, 2, so that's 2 bonds. And you have this double bond right here, which makes it count for 4 different bonds. Okay, so carbon is still satisfied by forming 4 bonds. However, they are not all single bonds. 2 single bonds and 1 double bond. Carbon can also satisfy its 4 bonding through forming 1 single bond and 1 triple bond, as we see here. So when we look at this one, carbon is forming 1 single bond with the hydrogen, On the other hand, it is forming a triple bond with another carbon. So when you do the count in total, that is 4 bonds for carbon. So it meets the stability, basically requirement for the number of bonds for that carbon can form. Um, Oxygen can also form multiple bonds similar to carbon. So when we looked earlier, we looked at the water, which it has 2 lone pairs and 2 single bonds. So generally, oxygen needs or must have 2 single bonds and 2 lone pairs, okay, in order to be stable. Or maybe it can form 1 double bond and 2 lone pairs, as we see in the O2. So when you look at the oxygen molecular structure, we can see there is two there is 2 single bonds, or what we call them a double bond, not 2 single bonds. It's a double bond, and 2 electrons, two lone pair electrons around every single oxygen. So this table here is really helpful to tell us exactly how many bonds every element can form and how many lone pairs there will be when that bond is formed. First, when it comes to the hydrogen, so we all know the hydrogen can form only 1 bond. We'll have 0 lone pairs at this point. For the boron, the most common is three bonds and 0 lone pairs. Example for this one is the BF3, right? BF3. When we looked at this one a second ago, so that was B with 3 fluorines and 0 lone pairs electrons. For the carbon, the most common one is 4 bonds. The count of bonds is 4. This can be through either 4 single bonds or 2 single bond, 1 double bond, or 1 single bond and 1 triple bond. At rare cases, carbon can form 3 bonds with 1 lone pair, but you don't have to worry about this one. I'm not going to bring any rare cases about the carbon. When it comes to the nitrogen, phosphorus, and arsenic, the most common is 3 number of bonds and 1 lone pair. Example for this one, the NH3. That's the one that we looked at a second ago as well. So that's with 3 hydrogens, right? So there's 3 hydrogens and the lone pair on the top of the nitrogen. Same thing if you were to study something like the PH3 or the ASH3, they would have the same behavior. Common one also, for the nitrogen specifically, you can have 4 bonds and 0 lone pairs of electrons. But this will require nitrogen to behave or be an ion or a cation in order to form the 4 bonds. And this one I am not going to bring in my exam as well. So doing the Lewis structure for ions, this is not going to be something that I will be covering, not in my lecture and not in my exams. So that is another thing you can cross out from your list on top of the rare of the carbon. So these things you don't have to worry about. For the oxygen, sulfur, and selenium, the common one is 2 bonds and 2 lone pairs, correct? So the 2 bonds for the oxygen can be either 2 single bonds, like the H2O, or 1 double bond, like the O2, which you will have 2 bonds, and the 2 lone pairs are always there, just like you see here and you see here. Common one for the oxygen, for the sulfur and selenium, you can also have 1 single bond and 3 lone pairs. That's for the common. For the rare ones, you don't have to worry about this one as well. I'm not going to be bringing anything about this. For the halogens, for the fluorine, chlorine, bromine, and iodine, there is always 1 bond, the possibility of forming 1 bond, and 3 lone pairs, just like how we see here. And we looked at that when we did the F2. So now let's try to dig in and try to do some Lewis structures. If you look at the book, I think the way the book explains how to do the Lewis structure is a little bit lengthy, and it requires some math element, and I know you guys are not really fan of doing math, so I'm going to introduce a little bit of a different way how to do the Lewis structure, and I think it's easier to follow, and chances to make mistakes hopefully is less. So let's do some examples on drawing the Lewis structure for a little bit more complex molecules. So first what we need to do is we need to draw the Lewis dot diagram for each atom in the formula. So we will look at the valence electrons and try to do the Lewis dot structure for these. And then we will essentially try to pair all unpaired electrons, and this is how the bonds are formed. Few things to consider: that carbon always take the center, and it is always your central atom in any structure, because it is the element with the highest number of bond formation, right? Carbon can form 4 bonds, okay? And then if there is no carbon in there, what we do, we go by the number of subscripts, or what we can we can focus on the number of non-paired electrons, and the atom with the highest number, of the most number of unpaired electron, will be at the center. Let's do some examples and start with the CH3Br. So first what we need to do is we need to determine our central atom, correct? Our central atom in this case is going to be the carbon, because like I said, in any chemical structure, if you see carbon, carbon is going to be your central atom all the time. That's a rule of thumb. So carbon is going to be in the center as my central atom. And then what else I have? I have 3 hydrogens, so that makes it 1, 2, 3 hydrogens, and I have another bromine. Now next thing, now I've determined my central atom. Now I need to do my electron, my Lewis dot structure for the electron, or electron Lewis dot structure. For the carbon, it belongs to group 4 in the periodic table, so it has 4 valence electrons. For the hydrogen, I think we all agree at this point that hydrogen has 1 single valence electron. For the bromine is part of group 7 in the periodic table, correct? So it has 7 valence electrons. So that makes it 1, 2, 3, 4, 5, 6, and 7 valence electrons. So what I need to do now, I need to pair the unpaired electron, basically like solving a puzzle. So what I have here, let's do this. So one electron from the hydrogen will go to 1 electron from the carbon. Another one will bond with the other electron. Another hydrogen will bond with another electron from the central atom of the carbon. And I have the last electron of the bromine. It is going to be connected with the last electron on the central atom, which is the carbon. So basically, we are looking for all non-paired electron and just drawing these arrows and try to solve the puzzle and pair these electrons. But this is not a legitimate way of representing a molecular structure. So what we need to do is we need to replace all these spaghetti lines with straight lines, correct? So what we do is we have the carbon and make it look more legible. We have 1, 2, 3, 4. I have 3 hydrogen, 2, 3, and I have the bromine. Something on the bromine that you have to show is the non-paired electrons. We have to see the non-paired electrons, okay? I've seen people always forgetting the non-paired electrons. So the non-paired electrons are important to demonstrate in any molecular structure that you do moving forward. Okay, so this is the Lewis dot structure for the CH3Br, or the methane bromide, methyl bromide. Okay, let's do a couple more examples. CH2O. So first what I need to do is I need to determine my central atom. Well, I have carbon and I have oxygen. Which one would be the central atom? Carbon would always be the central atom. So carbon is going to be at the center of my structure. How many valence electrons for the carbon? Look at the periodic table. Determine how many valence electrons you have. It is part of group 4. Then I have 4 valence electrons. So I'm going to have 1, 2, 3, and 4. Now I have hydrogen. I have 1 hydrogen. I have 2 hydrogen. and I have one oxygen, correct? How many valence electrons for the hydrogen? It has, oops. Hydrogen. How many valence electrons for the hydrogen? I have one electron, one electron. How many for the oxygen? For the oxygen, I have 6 valence electrons, correct? I have 1, 2, 3, 4, 5, and 6 electrons. That's because oxygen is part of the group 6 in the periodic table. So now I have lone pair, or I have single or unpaired electrons on the oxygen, on the hydrogens, and on the carbon, and I just need to connect all these, well, with my spaghetti lines, correct? So one hydrogen will go to this guy, another hydrogen will come to this one, and an oxygen would connect to this electron on the carbon, and I still have one non-paired electron down here, so this one is going to connect to this other electron on the carbon. All right, so now let's replace our squiggly lines with straight line to indicate the bond formation. So I'm going to have the carbon down here, and I'm going to have straight lines, 1, 2, 3. And I will tell you why it's 3 in a second. First, I have the hydrogen. I have a hydrogen up here, and I have a hydrogen up here. Now I have oxygen. But if we notice, oxygen bonded it twice to the carbon because oxygen has 2 non-paired electrons that bonded with the 2 non-bonded electrons on the carbon. So instead of a single bond, carbon and hydrogen will have a double bond between them. So oxygen will bond to carbon through a double bond. Something not to forget is the lone pairs on the oxygen, as we see here. So we still have these lone pairs or non-bonding pairs. 1, 2, 1, 2. So this is the structure for the CH2O. So first, again, I'm going to rehearse this for the one last time, I believe. I'm not sure if we have another example or not. We do have another example. So first, what we need to do is we need to determine the central atom. Carbon is always at the center. Second, count your valence electrons for the central atom as well as for the bonded atoms to the central atom. Okay. Look at the periodic table. Make sure to always preserve the lone pairs at the end when you do your structure. Connect these non-paired electrons to every single non-paired electron in the central atom, and that's pretty much would be your Lewis structure. I really think it's really easy, and if you think of it not as chemistry at all, I think it's just solving a puzzle. That's all, connecting dots. Let's do now the nitrogen diatomic molecule. So first what we need to do is we need to write down our 2 atoms, correct? Now in this case, we don't have a central atom because we're talking about a diatomic molecule, which is the nitrogen. So nitrogen, I will have a nitrogen, 2 nitrogens on both sides. How many valence electrons for the nitrogen? Nitrogen will have 5 valence electrons, correct? Because it is part of group 5 in the periodic table. So what I'll have 1, 2, 3, 4, and 5 valence electrons. Likewise on the other one, 1, 2, 1, 2, 3. Always start with single distribution of electrons and then go back and couple, just like how we did with the orbital diagram. I think that will prevent any mistakes. Now, I have 3 single electrons that they need to be paired up together. So what I need to do is I need to basically just connect them together. There is one here, and there is another one down here. Now, because this is not a legible way of writing a chemical structure, what we need to do is we need to replace these lines. So I will replace these squiggly lines with nice triple bond. Did I forget anything? Yes, I did, which is the lone pairs of electron. Never forget the lone pairs of electron, and this will be on the top. Okay, so this is the Lewis dot structure for the nitrogen. Okay, let's do another one. Let's do the CO2. Or you know what? I will leave this CO2 to you and submit this to me the next time I see you. Or even if you want to try to do that and just on a piece of paper, take a picture and email it to me. So this will be an extra credit. Okay? So do that on your own and submit it to me for extra points. So when it comes to isomers, isomers are substances that have the same molecular formula but has a different molecular structure. What does that exactly mean? So if you look at these two molecules, we have 1, 2 hydrogen, 3, 4, 5, and 6. So we have 6 hydrogens. We have 2 carbons, right? 1, 2. So we have 2 carbon. And if you look at the oxygen, we have 1 oxygen. If you look at the other molecular structure, what we have here, we have 1, 2, 3, 4, 5, and 6 hydrogens. So we have 6 hydrogens, and we have same number of carbon. So we have 1, 2. So we have 2 carbon, and as you see, also we have 1 oxygen. So they both have the same molecular formula, which is C2H6O, but they have a different molecular structure. Depending where the oxygen is falling. Is it between the 2 carbons? Is it on the side of the bonding only to 1 carbon? So we call these isomers. In many times, especially in pharmaceuticals, drug manufacturers, they try to target a specific isomer because our body, for example, pain receptors, they only accept or able to adapt to one specific isomer. So they might make the same chemical with the same molecular structure, the same molecular formula, same molecular mass, but the efficacy for that drug is very low because the isomer selectivity, it's very low. So our pain receptors, for example, it's not willing to adapt to that one or accept that isomer. So that's why drug manufacturer, they always try to be very selective, stereoselective with their isomers, because it really determines the drug efficacy. So just in case if you're curious why things are made in different isomers. So let's look at an example and see how the Lewis dot structure can give us 2 different molecular structures that are correct for one single molecular formula. In this case, we'll be looking at acetaldehyde, which is used to convert into the sedative chloral hydrate. When the reaction is conducted, the first step, chloral hydrate, of making chloral hydrate, acetaldehyde, can change to the other isomer. So the first one that we have here is the CH. The first molecular formula that we have here is the CH3CHO, and the second one that we have here is CH2CHOH. Now, if you remember back when we were talking about acid and bases, and we talked about how the hydrogen, the acidic hydrogen, are usually specified in the molecular structure or in the molecular formula to indicate that this hydrogen different from the others. So the molecular formula itself does give us some information and does give us some insight about how the molecular structure is going to look like. So if you look at both of these, we notice that the oxygen, one time it looks like it is connected to the carbon possibly, or in this case, it is connected to the hydrogen. But we can tell that the oxygen, it is forming different kind of bonds within that molecular structure, forming 2 different isomers. So let's try to do the Lewis dot structure for both of these and see how they would look different. So first, what I need to do, regardless if we're talking about the first or the second, we need to draw down our central atom, or atoms in the second, which is the carbon. So carbon is going to be at the center. I have 2 carbons. And the carbon will have the 4 valence electrons all the time. So 1, 2, 3, and 4. What else I have? I have 4 hydrogens in total. So what I will do is I'm going to draw my hydrogens. I have 1 with their valence electron, 2, 3. So here's my 4 hydrogen with a valence electron. I am left off with the oxygen, right? So oxygen will have to come here. Lone pairs on the side always for the hydrogen, for the oxygen, and I have the 2 single non-bonding pair on this side. So what I need to do now, I need to basically just connect these lines. So for the hydrogen, so here's hydrogen is going to connect with this one, and here's another hydrogen is going to connect with the single electron for the central atom for the carbon. Here's 2, and here's the carbon. Both they will have to connect to each other. So here's another line. I still have a single electron down here on the carbon, so this one is going to connect with this hydrogen. The next one that I have here is this hydrogen is going to connect with this carbon. Now what I'm left with a single electron here and a single electron on the carbon on this side, and I still have the 2 electrons of the oxygen. So these 2, they will connect together. So what is this? These spaghetti lines are going to give me. So the structure for this would look like this. I will have carbon. Let's do another color. So I'll have carbon in the center with a bond, and I have 2 hydrogens connected to that carbon. 1 hydrogen and 1 hydrogen. And another hydrogen. And I have a hydrogen connected to this carbon, and I have double bond of oxygen. Correct? That's where my double bond comes from. And then I never forget my lone pairs on the oxygen. So that is the first isomer for the acetaldehyde. Now, if you look at this molecular formula, there is a possibility of having another structure for the acetaldehyde. Let's try another one, and let's see what other isomer we can get. So what I will do first, I'm going to follow the same kind of logic. I'll have my carbons in the center, and I will have, oops, let's make this one bigger a little bit. And I will have my valence electrons, 1, 2, 3, and 4. 1, 2, 3, and 4. Now I have my hydrogens, which is 1, 2, there's the valence electron. And here's the valence electron for the hydrogen, single valence electron. Okay. And here is the oxygen. 2 electrons. 2 electrons. This is the lone pair. Oh, there should be a lone pair, another one here. And here is my single electrons for the oxygen. So now I need to connect these lines in a way that would give me a different isomer, but I have to consider the number of bonds for carbon, the number of bonds for hydrogen. All of these has to be satisfied. I can't just connect the dots and assume that this is the isomer. The structure has to be stable. Okay, so carbon will have the 4 bonds, oxygen will have the 2 bonds with 2 lone pairs, hydrogen will have the single bonds. All these has to be factored in, so we make sure this structure is stable. So what I will do is first I am going to connect these carbons together. What I will do also, I'm going to connect these 2 electrons together on the carbon. So now I have, later on, I'll have a double bond on the carbon. Okay? So now what I need to do is I need to connect my hydrogens. Remember, this electron here has already been involved in bond formation of a double bond. So I can't connect my hydrogen to this one. So this hydrogen will have to come and connect to this guy here, to this electron. This hydrogen will have to come and connect to this electron. Now I'm still left with an electron on this hydrogen, electron on this hydrogen, and I still have 2 electrons on the carbon. Okay? One of these electrons of the hydrogen is going to connect with the oxygen instead. And that's what we can see from this molecular formula. We can see the oxygen and the hydrogen are bonded together, correct? Now, what I can also now do, this electron, it is going to connect with the single electron on the carbon. And now this will still connect to the single electron on the carbon for the hydrogen. Okay, so now what I need to do is I need to replace all these lines with straight lines indicating the bond formation. So let's do that together and let's see how the isomer is going to look like. So first, I'm going to have my two carbons. Let's have this one up there. So here's my carbon, first carbon, my second carbon, but we decided to have a double bond between these two carbons. I have a hydrogen and a hydrogen bonded to this carbon. Let's look at the second carbon down here. So this carbon, it is connected to a single hydrogen, correct? And is connected to oxygen as well. And this oxygen, as we see here, is connected to a hydrogen. Now, never forget my lone pair or non-bonding pairs. So this is presumably my isomer number 2. Now, is this a stable structure? Can we count our bonds and make sure that the carbon would have 4 bonds? Yes, if I look at this carbon, for example, it has 1, 2, 3, and 4. It has 4 bonds. If I look at this carbon, it has 1, 2, 3, and 4. 4 bonds. Hydrogen is connected to single bonds. Oxygen is connected to 2 bonds, and still retained its lone pair of electrons. So this is a correct molecular structure. So this is isomer number 2. This is isomer number 1. Okay? And like I said, if you count the electrons, the bonding on this one as well. So carbon, it has 1, 2, 3, 4. Carbon, this carbon here, it has one double bond, that's 1, 2, 3, and this one is 4. Oxygen is bonded with 2 bonds, 2 lone pairs. Hydrogen is bonded to single bond all the way. So these are the 2 isomers for the acetaldehyde. So in the exam, if you do either ones, I'm not going to really deduct any points. As long as you meet the number of bonds for carbon and for hydrogen and for oxygen, you demonstrate to me that this is a stable structure, I will take it. I don't really deduct points for writing or drawing either isomers. Now, let's talk about geometry and see how we can anticipate or expect what kind of geometry a molecule will have based on the number of bonds, based on the lone pairs, and also we can predict the angles between the bonds. So the first geometry that we have here today is the tetrahedral. And every time we talk about tetrahedral, we have to mention CH4. Okay, because CH4 is a great example for the tetrahedral geometry, where you have the carbon sitting right in the center, and you have the hydrogens as far away as possible from each other to deliver a good stability for the tetrahedral structure. So when we do the Lewis structure up to this point, this is the way that we draw it. But in fact, if you look at a three-dimensional structure for the CH4, it will exist in a tetrahedral formation or a tetrahedral geometry. The wedges that you see here, all these wedges, they actually mean something. The solid wedges, it means that the hydrogen pointing toward you, so it's basically pointing at us. The dashed wedges, it means that it's pointing through the screen, so it's going in the back. Okay, so the tetrahedral is basically like a pyramid where the carbon is sitting in the center and the hydrogen is pointing upward. This delivers the most stable conformation or geometry for the CH4, which is the tetrahedral. Because remember, the hydrogens that are connected to the carbon, these are bonding pairs of electrons. Remember, the key word here is electrons, and these are all negatively charged electrons. They tend to be really repulsive to each other, so they repel from each other, and they're really large clouds. So they try to be as far away as possible from each other to be very stable. The tetrahedral delivers that stability. So the ball and stick model will look like this. The geometric sketch would look something like what you see here in the squared box. The angle between both hydrogen is 109.5, and likewise between this hydrogen and this hydrogen and this hydrogen and this hydrogen. So it's always 109.5 between all hydrogens and the central atom. Okay, that's why the tetrahedral is very stable for something like the carbon with 4 bonds. So what does that mean? Any atom that forms 4 bonds will have a tetrahedral geometry. Let's look at another one. So the trigonal pyramid, if you look at this one, it's pretty much like the tetrahedral, with the exception that we took out the hydrogen, that it was connected to the top on the upper side of the carbon, and that one is now replaced with the lone pairs for the nitrogen, because we well know at this point that nitrogen forms a 3 bonds, and 1 lone pair of electron that rests on the top of the nitrogen. So the electron geometry, in this case, something like NH3 or ammonia, will have 2 different geometries. First, what we call the electron geometry, which we call it also which is also known as the tetrahedral. Okay, so the electron geometry, that's the first one. It is a tetrahedral, and that basically is concerned about counting all the electrons, all pairs of electrons around the central atom. Please pay attention to this, regardless if it is bonding or non-bonding. So in this case, I have 1, 2, 3, 4. Right? So I have 4 pairs of electron around the central atom. If it is 4, that means tetrahedral. So the electron geometry is tetrahedral. When it comes to the molecular geometry, we only count the bonding pairs of electrons. Please pay attention, the bonding pairs of electrons. So in this case, we have hydrogen. We have 3 hydrogens and 1 lone pair. We're not going to count the lone pair at this point because we're talking about the bonding pairs. So this is bonding pair plus non-bonding pair. We're talking about electrons. In this case, when we do molecular geometry, we're talking about the bonding pair of electron. So the bonding electrons for the NH3, in this case, will deliver a trigonal geometry, which is essentially like a tripod with nitrogen on the top and 3 hydrogens at the bottom. The angle between every hydrogen is 107.5. Let's look at another one. This is the bent geometry. So the bent geometry, something like H2O. When we looked at the H2O, if you remember, we have oxygen in the center, and we have hydrogen, and we have the 2 lone pair of electrons. So the electron group geometry, which concerns about counting the pair of the bonding pair and the non-bonding pair, would give us a count of 4, right? Because we have 1, 2, 3, and 4. So the electron group geometry in this case is tetrahedral, remember, because 4 means tetrahedral. The molecular group geometry, on the other hand, we call that one bent, because we have these 2 lone pairs of electrons. They express a huge amount of pressure and strain on the bond of hydrogen and oxygen. It really pushes it inside, forming a bent shape, something like this. That's why we call it bent. Okay, the angle between the oxygen and hydrogens and the hydrogen is 109.5. Trigonal, planar. Planar is when you have the Lewis structure, something like the BF3, and you have no lone pairs of electrons, and everything is bonded to the central atom. the geometric sketch in at this point we call it trigonal a planar. The angle is 120, so something like the BF3 as you see here. Okay, so when we draw the BF3, it's the boron in the center, the fluorine on the sides. There is no lone pairs, right? So the boron is just sitting by itself. So a central atom connected with three, or has three bonding pairs of electron would form something like trigonal planar. So it has zero lone pair or non-bonding pairs of electrons. I will give you a table that covers all of this, so you don't have to worry about memorizing all of these. A linear, that is basically just a straight line. The angle will be 180, so it's a basic straight line, something like ethylene, as you see here, with a low structure that is just a single straight line with a triple bond between two carbons. The geometric sketch will be as you see here with 180 degrees angle. Okay, so how do we write a geometric sketch and make sure that we're not making any mistakes? First, what I would like you to do is I'd like you to box any atom in the low structure that bond to two or more other atoms. That means we're looking for the central atom. So this one, in this case, the nitrogen. So the nitrogen is connected to both oxygen and fluorine, two or more. So I'm going to box this one. Second, what I would like you to do, determine the number of electron groups for each boxed atom by counting the number of sides of that box that have bonds or lone pairs of electrons. So we're doing bonds and lone pairs. We're counting everything. So I'm looking for the nitrogen. So how many electron groups I have? I have one right here. I have a second one on the top, and I have three down here. I have three. The double bond, again, this counts as one single electron group. We don't count that as two. Same thing with the triple bond. I don't want you to be confused with that. So we have 1, 2, 3 electron groups. Next, we need to determine the molecular geometry by identifying how many of these electron groups are bonds, are bonding groups. Because remember, when we counted the first one, this is all the count of electrons, bonding and non-bonding. Now, to determine the geometry, the molecular geometry, we need to make sure that we're counting the bonding electrons only. So in this case, how many bonding electrons we have? We have 1 with the fluorine, and we have number 2 with the oxygen. So we have only 2 bonding groups. And we have 1 lone pair down here. So we have only 1 lone pair. And then we draw the general geometric sketch based on the electron group geometry. And then we fill in the group sketch with the atoms in the given Lewis structure. All right, let's do that together. Before we do this one, this is the table that I mentioned. This table basically delivers everything you need, and I'm going to give you this during the exam, so you don't have to freak out about memorizing all these geometrical sketches, about angles, so on and so forth, the naming, the nomenclatures, everything will be on this table. So what we do is we count the electron groups. Let's see how we can read this, because without the ability of reading this correctly, this is going to be useless. So first, what we do is we count the electron groups. If you have 2 electron groups, it is going to be linear. Angle is going to be 180. So you're going to count all the electron groups around the central atom. 2 bonding pair, and we'll have 0 lone pairs. The molecular geometry will also be called linear. So the linear, essentially, it doesn't matter if it is a group geometry or if it is molecular geometry. It will always have a linear shape. When it comes to the trigonal planar, the 3 electron groups, that's when the electron geometry has only All right, so let's look at this table and try to read it together, because if you are unable to read this, it's going to be useless, even if I give it to you during the exam. So when you're trying to figure the group geometry or molecular geometry, everything is going to be given to you in this table. These are the two things that you will be questioned to do: group geometry and molecular geometry. It's all based on the number of your groups of electrons. So it's you're either counting the group of electrons, how many groups of electrons, and then the molecular geometry will be based on the bonding groups of electron. So let's look at this one. So for linear, if you have total count of groups of electron is 2, it is going to be a linear. Angle will be 180. The bond angle will also, like I said, will be 80. This is how the sketch is going to look like, and it'll have 2 bonding group of electron. Linear generally doesn't have any lone pair of electron. Let's look at the trigonal planar. Trigonal planar will have 3 electron groups. The sketch will be, so the sketch would look like this. The angle, the bond angle, will be 120. If the bonding electrons equal to the number of groups, that means all the electrons around the central atom have formed bond, something like the BF3, will form trigonal planar. So the molecular geometry will have the same thing as the group geometry. If the bonding groups of electron is 2, while you have 1 lone pair, the shape will be bent. So we'll have something like this. Will look like a bent shape. When it comes to tetrahedral can go few different ways. So first, if you have 4 groups of electron, this will always be tetrahedral. The shape will be 109.5, will be as you see here, and the angles will be 109.5. Case number 1, if all the groups are bonding groups of electron, then the shape is going to be tetrahedral. Case number 2, 3 bonding pairs of electron, 1 lone pair of electron. This will be trigonal planar, something like NH3. If you have 2 bonding pair and 2 lone pair, it will be bent, something like H2O. So this is case number 2. This is case number 3. Everything on the exam, it is going to be coming from this table. So if you know how to use this table, I don't see any reason why you are unable to answer the geometry questions. Let's do an example together. So first, we write the name of the electron. We write the name of the electron group geometry around each atom that has 2 or more atoms attached to it. So as I did earlier, the nitrogen, it's going to be our central atom, correct? Because it is bonded to 2 or more, it has 2 or more bonds. Now we need to count our electron groups. Electron groups, that means all the electrons, bonding and non-bonding pairs of electrons. How many I have? I have 1 with the fluorine, I have a second one as a lone pair, and I have a third one with the oxygen. So in total, I have 3. If I go back to my table, trigonal planar, because my electron group indicate it is going to take a shape of trigonal planar. It is 3, all of them. So then the way I would do this, I would have nitrogen in the center, my central atom. I would have oxygen down here, and I would have fluorine down here, correct? So let's see if my molecular geometry will be different. So my group geometry is 3. My group geometry, I have 2 bonding pair, and I have 1 lone pair, and that's exactly what I have down here, because I still have my lone pairs of electron as you see it on number 2. So my 2 lone pairs of electron is going to rest on the top of nitrogen. So the molecular geometry will be bent. Group geometry will have trigonal planar. This is molecular geometry. The angles between both of these, as you see here, it is going to be a 120 angle. So this is the group geometry. Let's do now the methyl bromide, which is a molecule that we just did the Lewis structure a few slides ago, correct? And we have concluded then that for the methyl bromide, let's delete this one. For the methyl bromide, we have carbon with 4 bonds, 3 of which is hydrogen, and one that is a bromine. And in terms of the bromine, we always have to make sure that we are displaying our non-bonding pair. Now, the non-bonding pairs of electron that is sitting on the bromine, it is really negligible, and we don't really consider it when it comes to the geometry of the methyl of the methyl bromide, because again, when we do the geometry, it is all in terms of the central atom. Okay, so if there is any non-bonding pairs on any of the terminal atoms, it is not going to be our concern when we are trying to figure out the geometry. But we still have to show the lone pair on the non-bonding pair of electrons. So first, what we need to do is we need to figure out the group geometry. So that's our first task here. So the group geometry, that is basically determined based on all the count of electrons or the pairs of electrons, regardless if it is bonding or non-bonding. So we are focused on the central atom, and we would like to count the pairs of electron that surrounds the central atom, and based on that, we will determine the group geometry. So first, what we have the first pair of electron between carbon and hydrogen, second between carbon and hydrogen, 3 between carbon and hydrogen, and here's the fourth one between carbon and a bromine. So what we can see here, we have 4 pairs of electron, and they all seem to be bonding electrons. Okay, so for the group geometry, since we have 4 groups or 4 pairs of electrons, this will be tetrahedral. Correct? If you go back to our table here, again, we're talking about 4 pairs of electrons for the group geometry, so that is going to be tetrahedral. Let's go back now and try to figure out what is the molecular geometry. So for the molecular geometry, now, if we have any non-bonding pairs or lone pairs of electron on the central atom, that's where my count of, that's where my group geometry will be different from the molecular geometry. So if we go back to our table here, and for the tetrahedral, as we see here, we have 4 for the group of electrons, so that would be tetrahedral. And then we look here on the bonding groups. How many bonding groups do we have with a CH3Br? We have 4 bonding groups, correct? Because when I look at the CH3Br, I don't see any lone pairs on the central atom. So all the pairs of electron around the central atom are bonding pairs of electrons. So the molecular geometry as a result will be tetrahedral as well. Now, next thing what we need to do is we need to draw the tetrahedral. So with the tetrahedral, what we have the carbon in the center. We have 1 hydrogen. Actually, let me change the color. So let's do black. So we have carbon. So we have carbon in the center. We have hydrogen. We have another hydrogen. And we have a wedge with solid color. And we have another wedge pointing this way. Now, here we have the hydrogen, and we have here the bromine. The angle here is 109.5. So if you go back to our geometry here, tetrahedral geometry, it is 109.5. And the molecular geometry, as well as the group geometry, is the same because we don't have any non-bonding pair. Now, something I want to point out, you might see in some books, they have the bromine sitting up here and the hydrogen sitting down below. The reason why, because bromine is bulkier than the hydrogen atoms, correct? The hydrogen is very small and tiny with only one single electron that is already bonded. The bromine with 6 non-bonding pairs of electron, it tends to be bulkier and bigger. So being on the top of carbon gives the bromine much more space to essentially expand its muscles. Because compared to the hydrogen down here, it's a little bit more cramped. So the bromine will be more stable above the carbon. Okay, so the molecular geometry and the group geometry is the same. Let's try to do a couple more examples. Let's try to do the CH2O. So with this one, carbon, as I said earlier, carbon will almost always be the central atom. So in case where we have the carbon and oxygen, like in this example, where both are single atoms in the molecular formula, you don't have to think about it. Carbon will be your central atom, okay? So first what we need to do is we need to figure out our Lewis structure, or I believe we also did that one earlier. And with that one, we have determined that carbon was in the center, correct? And we have oxygen up here with a double bond, and we have hydrogen on the bottom, correct? So now what we need to do is we need to determine our group geometry. So number one, let's try to find our group geometry. So our group geometry would count all the, now again, these are non-bonding pairs for the oxygen. Now our group geometry, that means all the pairs of electron that surrounds the central atom, which is the carbon, regardless if it is a paired or non-paired electrons. So from what I can tell here, looking at the carbon, I see there is a hydrogen here, so that is the first pair. There is another hydrogen here. There is an oxygen up there. Now, even though there's a double bond, which means there is 2 pairs of electron essentially, this still counts as a one single bond when it comes to counting bonds for the geometry. Okay, so this is not counted as 2 bonds. Okay, so in this case for the carbon, I have 1, 2 bond, and here's a third one, correct? So let's go back to our table. So according to our table, if we have a 3 electron group, that means it is trigonal planar. So I'm going to go back. Oops. I'm sure where this line came from. Let's go back to our molecule, and our group geometry will be, according to my table, trigonal planar. Let's now try to find out what is our molecular geometry. It is going to look like. Now, the only time where the molecular geometry is not going to be the same as the group geometry if there is lone pairs of electron. Now, the question here, do you see any lone pair of electrons sitting on the central atom, which is the carbon? The answer is no, because carbon does not have lone pair of electron. It never does, okay? All the electrons on the carbon, on the central atom of carbon, always participate in bond formation. As a result, my molecular geometry will be the same thing as the as the group geometry. In other words, it's going to be oops, I want that one in red. Trigonal planar. So if I want to draw this one, it essentially won't be so much different than what we just did earlier. It is going to have a carbon in the center, 2 oxygens. Never forget your lone pairs of electrons. And then you have hydrogen down here, and you have hydrogen down here. This is trigonal planar. Now, the only thing that is missing here is the angles between the carbon, between the hydrogens and the oxygen. And in this case, you can get this one from the table as well. For the trigonal planar, the angle is always 120. Okay. So you'll have to indicate that on your molecular geometry as well as your group geometry. So the angle here is going to be 120 degrees. Let's try to do now the geometry for nitrogen. For nitrogen now, if you remember when we did the Lewis structure, nitrogen, the diatomic molecule, looked like this with 2 lone pairs of electron, 1 on each of the nitrogen atoms. So how can we do the geometry for this? Can you tell if there is a central atom or not? The answer to this is there is no central atom, right? Because in order to figure out the geometry, the group and the molecular geometry, that atom has to be bonded to 2 or more other atoms. Neither of these nitrogens are bonded to 2 or more. This nitrogen is bonded to a single nitrogen. This nitrogen is bonded to a single nitrogen. So in this case, there is no geometry. Okay? So if there is no central atom, that means there is no geometry. Remember, in order to sketch the molecular or the group geometry, that central atom has to be bonded to 2 or more other atoms. If that condition has not been met, then there will be no geometry. So now let's do the carbon dioxide. Now, when we did the carbon dioxide Lewis structure earlier, it was C double bond O on both sides with oxygens on both sides of the carbon, correct? And if you are not sure, you can go back to the carbon dioxide Lewis structure. Now, we cannot afford to forget our lone pairs of electrons. So here's my lone pairs of electrons sitting on both oxygens. So next step, what I would like to do is I'd like to identify my central atom. Here is my central atom right here. My central atom is bonded to 2 or more other atoms, which means I can or I should be able to predict the electron group geometry as well as the molecular geometry. So first what I will do is the electron group geometry. For the electron group geometry, we need to count how many electron groups around the carbon, bonding and non-bonding. How many I have? I have 1 right here, and here is the second one. So I have 2 groups of electrons around the carbon. When it's 2, I'm going to go back to my chart. If it's 2 groups of electrons, that makes it a linear. So the group geometry is going to be linear. So this is going to be a linear geometry. Okay. Let's do now the molecular geometry. Do I have any non-bonding pairs surrounds the carbon, the central atom? No. The answer is no. So that makes my group geometry same as the molecular geometry. So it's going to be linear as well, similar to the group geometry. So now let's try to draw a linear molecule. C, carbon at the center, oxygens on both sides, lone pairs down here. And a linear molecule, it's basically just a nice straight line with a central atom in the center and both atoms on both sides. Now we'll have to indicate our angle, and that is 180 degrees. So always when you draw your structure, you need to identify your angles in your molecular or group geometry, both of them. Now let's do this challenging one. Now, for sure, this is not going to come on the exam. I will never question you on something like that, but I think it's a pretty interesting one to look at. So let's do this one together. So in order to figure out what is the molecular geometry for this molecule as a whole, what we need to do is we need to identify our central atoms. So first, here's my first central atom for this carbon. Here's my second central atom. Here's my third one. And I have another central atom for the carbon, because remember, carbon is almost always the central atom. And now I have an oxygen that is a central atom because it is bonded to two or more atoms. It's bonded to two carbons on both sides. And now I have another carbon that it's also a central atom. So what we will need to do, we will need to figure out what is the molecular geometry around every single central atom that I just highlighted here. And overall, once we're done, this will be the geometry as a molecule for the entire molecule. Okay? So let's follow the rules that we have been just working on since we started talking about geometry. So for the first one, let's do the first one, the first carbon. So I have carbon right here, and this carbon is connected to 1, 2, 3 groups of electron, and they are all bonded, correct? So when we have three groups, three electron groups bonded to the central atom, and there is no lone pairs, that makes it trigonal planar, correct? So I have this geometry would look like this. I have one carbon here, and I have another we have one bond here, another bond here, and we have a double bond with another carbon, which we are going to focus on in a second. But overall, there's going to be a hydrogen and a hydrogen, and the angle here has to be 120 degrees. So here's my first geometry on the first central atom. Let's do the second one, which is this one here. Okay, so on the second carbon that I have here, the case is very similar, because as you see here, we have three electron groups. We don't have any non-bonding pairs of electrons, correct? So this one is going to be another trigonal planar. So it is going to have a carbon up here, and it's going to have another carbon down below. Now, this carbon, it has a triple bond, and while we are looking at it, might as well try to figure out what is the geometry for the third carbon atom. And as we see on this one, we have in total two group geometries. This triple bond will be counted as one electron group. So we have one and we have two electron groups. That makes it linear, correct? Because we don't have any non-bonding pairs. So this will be 180 degrees with nitrogen on the side and lone pairs located on the nitrogen. Okay, so let's move along. What do we have here next? We have the fourth carbon here, which is equivalent to this one down here. So this one will have a double bond, correct? Here's my double bond, and here's my oxygen, and here's my two lone pairs of electron. So this carbon here, it is connected to an oxygen. Okay, so this oxygen has four electron groups in total, correct? But two of those electron groups are non-bonding pairs, lone pairs of electrons, which means this geometry, this molecular geometry for that central atom, the oxygen right here, this will be a bent geometry. So this will have oxygen, or we can probably draw it this way too. So this will have oxygen here with two lone pair of electrons here. And the angle is 104. I know this one is not on the chart, but just to kind of put that there for ha-has. So the angle is 104. What is the group geometry for this one? This was supposed to be a tetrahedral. Because we have two lone pairs, this changes to bent. Okay? So this is bent. Now we're moving along to the next carbon that I have here. So this is my fifth, or this is actually my fifth central atom. This one, the sixth central atom. I'm going to try to figure out the geometry. So for this one, I have carbon, correct? And this carbon is connected to it has four electron groups, and there is no lone pair surrounded. So that must be a tetrahedral. So this will have hydrogen. Let me clear this one. This will be, let's write it here, bent, because I'm going to need some space. Another hydrogen. Oops, not sure where this line is coming from. Here is a hydrogen. And I have a solid wedge. And there is another wedge that's pointed inside with another hydrogen. The angle here is 109. Or 109.5, I believe. So this is the overall geometry for this molecule. Now, I'm not going to be bringing something for the exam similar to this. But this is, I think, an excellent example to try to understand geometry, because really it sums up almost everything that we have been just talking about. So far, or once we complete everything, we have trigonal, planar. For this one, we have a bent down here. We have linear. And we have tetrahedral. And I know we have another trigonal planar here. Okay? So with this example, I think this concludes this unit. And it also concludes the course overall. I hope you found this interesting, especially with this last example. And certainly, if you have any questions, make sure to reach out to me, and hopefully I'll be able to clarify things.